Okay, guys, welcome back. So what we have seen in the last couple of lectures are basically many of the tools that are offered by constraint programming. So what I want to do in the next couple of lectures is actually tell you how you can use these tools to do interesting things. Okay? And the first thing today is going to be about symmetries. Okay? So a lot of problems in practice have natural symmetries. Okay? So there are things that are just, the same. And therefore, you want to actually exploit that information to do search in a better fashion. So essentially, you want to break these symmetries such that you get always a smaller search tree. Okay? So what I'm basically saying here is that there are a lot of problems with a lot of symmetries. Naturally, when you express them, they have these symmetries. And exploring this symmetrical part of the search trees is completely useless. If you have explored one part and then you explore the part which is really symmetrical to it, it's just a waste of time. If there was no solution to that part, there will be no solution to the symmetrical part. Okay? So there are many kinds of symmetries. In these lectures, I will basically only talk about two of them, variable symmetries and value symmetries. Okay? And the way we're going to break these symmetries in this lecture is using symmetry breaking constraints. There are other ways to do this, but this is the only one thing that I want to focus, one thing at a time. Okay? And so what I'm going to talk about is how we can break variable symmetries and how we can break value symmetries. So once again, right? So this is an introduction. There are thousands of papers on this topic. Okay, thousands of ways of doing this, but I'll give you an introduction to these techniques. Okay, so we'll start with variable symmetries, and I'm going to introduce a very simple example, which is called balanced incomplete block design. Okay, BIBDs for those of us who actually work on this. So the input is a set of 5 numbers that probably mean nothing to you. Okay, so VBRQL. Okay. Now, forget about them. Okay, so what we are really looking for is a matrix, okay, 0, 1 matrix. So the value in that matrix are going to be 0, 1. So we'll have 0, 1 decision variables in a sense. And the matrix is of size VB, okay, V rows, B column, okay. And what we want is that this matrix satisfies 3 kinds of constraints. The first one is that the number of 1 on every row, okay, of that matrix has to be R. The number of 1 on every column has to be K, okay? And then the scalar product of every 2 rows, okay, has to be exactly L, okay? So this is, for instance, a simple example of a BIBD, okay? So this is a BIBD which has a value 33221, okay, 33221, okay. So that means that it has 3 rows, okay. You can see them. You have 3 columns, okay. And then on every row you see exactly 2 ones, sorry. So that's because you have a 2 over there. 2 ones, okay. And on every column you have also 2 ones. And when you do the Cartesian product of every 2 rows, you will have exactly the value of that Cartesian the value of that scalar product, sorry, is going to be exactly 1, okay? Which essentially means that if you do the intersection of these guys, they have only one position where they intersect, okay? So that's what we want to do. We want to find, BIBDs like this, okay? Now this is, so why are we interested in this? And one of the reasons is that this is an example of combinatorial design. There are a lot of people searching for these kinds of things, and what they always have is a lot of symmetries. And I want to show you that on a bigger example after showing you the model. Okay, the model is actually very simple, right? We are looking for a matrix of 0, 1 variables. Okay, so essentially the decision variable are going to be M, I, J. Okay, telling you what is the value at position I and J in the matrix. And then essentially the constraints are going to be really simple, right? So the first set of constraints are going to express the number of 1s that you want on every row, then the number of 1 that you want on every column, and then the last constraint is a little bit more sophisticated. It's basically computing the scalar product. What you see over there is basically you take the product of MIX and MJX, okay? So that basically means I take row I and the column X. I take, row J and value and column X. I do a logical AND between the two, okay? And that's going to give me a 1 if both of them are 1, okay? And essentially what I want is that the sum of all these things in this particular case are going to be equal to L. I put a 1 in this example because that was essentially the example that I've shown you before. So this is a bigger BIBD, okay? So this is 7 rows, 7 column, okay? I want 3 ones on every column, 3 ones on every column, 3 ones on every row, and I want once again that the scalar product be equal to 1, okay? Now this is a beautiful solution, but now you're going to see all the symmetries, right? So if I take, these 2 rows and I swap them, okay, what do I get? I get another solution to the BIBDs, okay? So essentially, every time I take two of these rows and I swap them, I still have a solution, because essentially, there is nothing distinguishing these rows, okay? The only thing that I said about the rows is that they have to have a certain number of R, and then when I take two of them together, the scalar product should be a value, okay? There is nothing that tells me that row I is different from row J, okay? So essentially, every time I permute them, I have a solution. Plenty of symmetries, right? So now you look at the columns, and this is exactly the same. There is nothing specific about column I and column J, right? So I can swap them, and then I get another solution, okay? And so that's what the drawing here is basically showing you, okay? So in a sense, at this point, I told you that, I can swap every column, I can swap every row. And so what I want is to avoid exploring all these set of configuration. I want to find, solution without exploring them all, okay? Otherwise, I could try a particular row and then another row, and then I could swap them and try again. And if there are no feasible solution for every two of them, I would essentially explore the search space twice, okay? So how do I break these variable symmetries? So a very, very nice way of doing that is actually imposing an ordering of the variables, okay? So in this particular case, so we are looking at the rows, and we want to make sure that the rows are essentially lexicographically ordered, okay? We want the first row to be lexicographically smaller than the second one, and the second one is smaller than the third one, which is smaller than the fourth one, and so on, okay? So I want to impose a lexicographic constraints on the various rows. What does that really mean, okay? So look at this thing, okay? So what you see there is A and B, okay, which are basically two of the rows, okay? And I'm going to say that A is smaller than B lexicographically if its most significant value is smaller than the most significant value of B, okay? So this is the case in this particular example, okay? So I have a 0 and a 1, which basically means that in this particular case, A is smaller than B, okay? But it may be the case that if I had a 1, it may be the case that these two guys are actually the same, and that's what you see in the next example here, okay? So in this particular case, you see that both have a value 1, so I can't decide at this point which one is lexicographically smaller than the other one. I move to the next element, and then I see a 1 and a 0, and what that means in this particular case is that A is actually lexicographically greater than B. Okay, so in this particular, so this is essentially what the lexicographic order is telling you. Compare the first two. If this guy is strictly smaller than the other one, you know that A is smaller than B. If they are equal, move to the next digit. If it's smaller or equal, okay, it's smaller. If it's greater or equal, it's greater, and so on and so forth. Okay, so that's essentially imposing a lexicographic constraints on these guys. Okay. Now, in this particular case, you see these guys. Okay, so this is essentially a solution. Now, this solution is not lexicographically ordered. Why? Because I have a 1 here and a 0 there. I know that this guy, the row 2 is not lexicographically smaller than row 3. Okay? So this is on the other side now. Okay? So this is a lexicographically ordered solution. You see that the first row is lexicographically smaller than the second one. Why? Well, look at this number. This is a 1. On top, you have a 0. Okay? You look at the next row. It's lexicographically greater than the previous one. You have a 0 there. Oh, you have a 1, and this guy has a 0. And so on and so forth. Okay? So this is essentially a solution now, which is lexicographically ordered. And that's what I want to search for. Okay? Because I'm removing all the symmetries. Now, I can't swap these two guys. Okay? Because this guy is lexicographically greater than that. So I reduce the search space tremendously. Okay? Now, in this particular example, okay, so what I want to do as well is actually breaking also the column symmetries. Okay? And actually, this is an interesting problem because I can break both the rows and the column symmetries at the same time and preserve, at least one solution per symmetry group. Okay? So that's what you see over there. Okay? So you see that this column here, okay, is not lexicographically smaller than this one. Okay? So why? Because you see, where am I? So you see a 1 over there and a 0 there, okay? So therefore, you have to essentially order them as well. And now you see these two columns there, and you see that they are lexicographically smaller than each other. Well, the leftmost is lexicographically smaller than the right one. Okay? So in a sense, what I want is to impose this lexicographic order on the rows, and impose a lexicographically order on the column, and search for the solution satisfying these lexicographic constraints. So essentially, the only thing that I have to do in this model, okay, is basically add, for every pair of rows, a lexicographic constraint. Okay? So this is a constraint taking all the elements of the row, of row I, and then all the elements of row I plus 1, and I'm basically saying that row I has to be lexicographically smaller than row I plus 1. Okay? And of course, I'm going to do the same for the next thing, which is row I plus 1 has to be smaller than row I plus 2, and so on and so forth. Okay? And I do the same for the column, and then essentially I have all the rows and all the column in a lexicographic order. Now, this constraints is actually very efficient to implement in practice. You can find feasibility very fast, and you can prune and achieve the optimal pruning very fast. This is one of the interesting global constraints that we have in constraint programming. Okay? So that's basically, how we can break variable symmetries. A lot of the techniques for breaking variable symmetries are following a similar pattern. Okay? Now I want to move now to value symmetries, and I want to reintroduce these beautiful actors. We were missing them, right? And so the problem is going to be different, though. Okay? So it's going to be a scene allocation problem. And this time we don't care about marrying these guys. What we want is actually making a movie. Okay? That's what these actors do for a living, right? And so this movie has a number of scenes that it has to shoot. And, an actor plays in some scenes and not in some others and things like this. And we have a very strong constraint, which is that at most K scene can actually be shot on a particular day. Okay? So you can shoot K scene per day, not more than that. Okay? Now, every actor is paid by the day, whether he shoots one scene on that day or, K scene on that particular day. So as soon as the actor is on the set for a particular day, you have to pay his fees. And of course, these actors have different fees, right? So that's what makes the problem interesting. Okay? So the objective is, of course, you're the producer of this thing. You want to minimize your cost. Okay? So you want essentially to schedule the actors such that they don't spend, too much time on the set, and you cluster the scenes in which they appear at the same time. But of course, different actors are playing in different scenes, so you have this tension. Okay? And of course, they have different fees. So how do we do that? Okay? So I'm going to show you the model in a moment. But before that, think about it. What are the symmetries that we have in this problem? Okay? Obviously, these actors are different, right? So, you can't tell George Clooney that he's the same as Clive Owen. So it's not going to be the actors. So it's not going to be that. So the scene are going to be different as well. They will have different types of actor. So there is no symmetries on the scene. So what are the symmetries? Okay? So the symmetries are going to be on the days. Okay? So essentially the days in which, the scenes are going to be shot. Okay, so this is the model. Let me go over the model such that we can understand the symmetries afterwards. So what you have is a set of scenes, you have a set of days, you have a set of actor. Every actor is going to have a fee. That's how much you pay the actor per day. Okay. Now we also know that every scene will have a set of actor. Okay. So that's what you see over there. Okay, and then we're going to compute a particular value, which are the scene in which an actor is actually appearing. This is going to be important. We derive this information from the information that we have about the scene. And then the decision variables, you see them there. Okay, it basically specifies for every scene which is the day during which the scene is going to be shot. Okay, so essentially for every scene you have to find which day is going to be shot. Okay, so what you have there are two things, the objective function and then the constraints. The constraints is very simple. It's kind of an all different constraint. It's a generalization of that. It's a cardinality constraint. And what it says is that, if you look at the array shot, okay, so what we know about that array is that we want at most 5 in this particular case. So every scene, every day we'll be able to shoot essentially 5 scenes. So every day I can shoot exactly 5 scenes. That's what this constraint is actually expressing. Now, once again, this is a very interesting constraint, global constraints in constraint programming. It can be, test for satisfiability very efficiently and prune optimally. Now, the objective function is also very interesting. What you are doing is that you look at every actor, okay? You look at every day, and if the actor is actually shooting on that day, you will have to pay its fee, okay? So you see the fee over there. And this expression that you see there, which has the reify constraints, is basically looking at all the scene in which the actor is actually playing and seeing if that scene is actually played on that particular day. Okay? So for every day, every actor, you look if the actor is actually playing a scene on that particular day. And if that's the case, you have to pay the fee. Okay? So that's essentially the model. Okay? And as I told you, in this particular model, we have value symmetries. The days are the same. So in this particular model, I haven't told you that Tuesday is different from Wednesday. For this actor, it doesn't matter. Okay, Thursday is the same as Monday. Okay, so in a sense, if I have a solution, okay, where we have a bunch of scenes which are played on day 1 and a bunch of scenes which are played on day 2. Oops, you don't see me, right? So then essentially you can swap these two things and you still have a solution. So these days are completely interchangeable. Okay? So I can't distinguish them. So in a sense, no, I want to break these symmetries. Okay? So I know that if I have a solution, any permutation of the day is going to be also a solution, but I don't want to explore it. How am I going to do that? Okay? Now, this is the reasoning. Okay? So look at the first scene, S1. Okay, I want to schedule that scene. Okay, I have, let's say, these 5 days, Monday to Friday. Which day am I going to schedule that scene? Okay, which day do I have to consider? Well, there is only one day that I need to consider, right? Okay, so, and this is the first day, let's say day 1. Why? Because at that point, all the days are the same. Okay, whether I choose Monday or Tuesday or Wednesday, there are no difference between them. So the first thing, I can decide forever that I'm going to schedule it on day 1. It doesn't do anything. Okay? Now let's look at the second day. Okay? So the second day, let's look at the second scene. Okay? The second scene, where can I schedule the second scene? Well, I can schedule it on the first day, right? So that's like the scene that I just scheduled. And maybe that's interesting because there are a lot of common actors. Or I can decide to schedule it on a day where nothing is scheduled yet, okay? Which is, let's say, day 2, day 3, day 4, day 5, okay? So they are essentially, but day 2, day 3, day 4, day 5, they are all the same at this point. I can't distinguish them. So essentially the 2 days that I have to consider are day 1 and then day 2, let's say. Only one of the other days, okay? So I have only 2 days, okay? So in general, okay, so if I look at a particular scene, okay, the only thing that I have to do is to look at the days in which I have already scheduled something. Okay, those I have to actually consider. Okay, and then I can choose one new day, a day where nothing is scheduled. And so if you do that, you remove all these value symmetries. Okay, so once again, this is easy to do. You take the model, okay, and what you do is you add these beautiful symmetry constraints here. Okay, so what do they say? They say that the scene 1 is to be scheduled on day 1. No brainer, right? So we knew that there was, absolutely no distinction between the various days at that point. And then the other constraints is basically taking all the other scenes, and what is it doing? It's basically looking at the days which have been scheduled for the previous variables, and then adding a new day. Okay, so the new day that you see there, this beautiful +1 there. Okay, so that's essentially what you're saying. You're saying the scene 1 is equal to 1, and the next scene, let's say scene S, has to be smaller than all the days which have been scheduled before plus 1 new day. Okay, and so essentially what you are doing in this model is stating these constraints that are removing all the value symmetries. You will never explore the fact that scene 1 can actually be scheduled on the second day. You will never explore the fact that scene 2 could be scheduled on the third day. Okay, so that's how you can break symmetries. Now this particular technique is very useful in practice. It has one limitation that I will talk about later in the class, and that you can actually remove that limitation by being a little bit clever. But I will come to that later on. Okay, that's it.